Okay, so we're getting ready to move into the fundamental theorem of calculus. And before we do that, we need to understand some basic properties of definite integrals. So that's what we're going to explore in this video. They're pretty simple to understand, but they're also very useful when you go through manipulating definite integrals. So the first thing I want to look at is the integral from a to b of the function f of x with respect to x. And the idea here is that this variable x, in this case, is not significant really at all. All it means is the area under the curve, if this is x and this is your f of x axis, then all it means is the area under the f curve from a to b, okay? This area does not really depend on what this variable is. So this definite integral could be written using any independent variable you want because the f function graphs the same no matter what we call the independent variable or the horizontal axis, okay? So you could integrate f of x with respect to x or f of t with respect to t or f of theta with respect to theta. It does not matter what your independent variable is. The output of each of these definite integrals is exactly the same and has the same meaning. So really you could think of the variable here as sort of a temporary variable, just something to notate the function, okay? So that's the first property we'll look at of definite integrals. The independent variable is not terribly significant. As long as the variable here matches the variable here, that's what's important. The next one is also pretty simple. If I integrate a function from a to a, from a constant to itself, then the area under this function, when there's no change in your start point and end point, that area is going to be 0. Integrating from a constant to a self just results in a 0 area, okay? Now this next one is interesting. We're going to look at the relationship between the integral from a to b of f of x compared to the integral from b to a of f of x, okay? And so if we look at this, and for simplicity, let's assume that this is our f function, and let's assume that a is less than b. So this first integral is representing the area of this curve, okay? Now what's sort of hidden in this integral is, remember, it's a limit of a sum of areas of rectangles, okay? So if you remember, the width of those rectangles is b minus a. You take your big value b minus your lower value a, and you divide it into pieces. So you do b minus a basically to help you get the width of each of the rectangles. That's assuming b is bigger. That's assuming b is your upper limit. If you make the lower number, a, your upper limit of integration, then now when you calculate those widths, you do a minus b. You do the top minus the bottom. But you can see if you do a minus b, you're going to get a negative width for each rectangle. So the relationship between these two, when you flip your limits of integration, is they are opposites of each other. So you could say that the integral from a to b is the negative integral from b to a, or vice versa, the integral from b to a is the negative integral of a to b. They're opposites of one another in either case. And so sometimes it's beneficial to flip your limits of integration and introduce a negative if needed. So that's our third property that we're going to look at. Last, probably one of my favorites is if I take an integral of a function from a to b and I add to that the integral of the same function from b to c. So if you imagine what that looks like, let's draw a picture of that. Let's say this is a, this is b, this is c. For simplicity, we're assuming they go in order. They don't have to. And then we've got our function like this. And if I want the integral from a to b of this function, that's this area. And if I want the integral from b to c of this function, that's this area. And you can see that if you add those two areas together, then what you get is you get the area of all of this. And so the sum of these two integrals, because the upper limit here matches the lower limit there, ends up being just the integral of the function from a all the way to c of that function. Really love this property. It makes it fun when you're manipulating these integrals to try to make upper limits of integration match lower limits, because if you can do that, you can put them together. Similarly, if you've got a function that has a problem between a and c, you can split the integral apart wherever that problem occurs. If it occurs at b, then you could split it into two separate integrals. Sorry, I think I pointed at this b. But you can split it at the problem area at b and help you split it into two integrals that are easy to do. Okay? So those are some really basic properties of integrals you'll need to know as you move forward in calculus, and specifically for the fundamental theorem of calculus.